Okay, good morning. Class begins. Last time, we have learned the chapter 2 about the physical layer. We will study these points. The physical layer is the foundation on which the network is built. The properties of different kinds of physical channels determine the performance of the communication channel. For example, throughput, latency, the error rate. So the physical layer is the foundation of the network. So if the physical channel have a higher performance, then the network service will be of higher QoS, higher quality of service. So the physical layer is the foundation of network architecture. Information can be transmitted on wires by varying some physical property, such as voltage or current, by representing the value of this voltage or current as a single valued function of time, ft. We can model the behavior of the signal and analyze it mathematically. Then we introduce the bandwidth. Bandwidth to electrical engineers and to computer science. The bandwidth, the concept of bandwidth has different meanings. To electrical engineers, analog bandwidth is a quantity measured in hertz. While to computer scientists, digital bandwidth is the maximum data rate of a channel, a quantity measured in bits per second. So there is a different meaning of bandwidth to different person. That data rate is the end result of using the analog bandwidth of a physical channel for digital transmission. And the two are related. So we will discuss the next section. So it will be clear from the context whether we mean analog bandwidth or digital bandwidth. Since the computer deals with digital information, so computer scientists consider the data rate of digital transmission. So it will be clear from the context. Now we should remember, we should understand this Nexus theorem. Nexus theorem states this equation: maximum data rate to computer scientists, the maximum data rate, right? So maximum data rate equals 2b times log 2v. Unit is bits per second. For example, noisiness 3 kilohertz. So the noisiness, Nexus theorem states the maximum data rate of a noisiness channel. So a noisiness 3 kilohertz channel cannot transmit binary signals at a rate exceeding 6,000 bits per second. So the maximum data rate is 6,000 bits per second. Here B equals 3,000. B is 3,000 hertz. V is 2 level. So the binary signal. So here V is 2. Here B is 3,000, 3 kilohertz, 3,000. So 2 times 3,000 log 2. So the maximum data rate, we get 6,000 bits per second. We should remember, we should understand this equation of Nexus theory. Now, in 1948, Claude Shannon carried Nexus' work further and extended it to the case of the channel subject to random noise. So it is not about noiseless channel, but random noise with random noise. So Shannon's major result is that the maximum data rate or capacity of a noisy channel whose bandwidth is B hertz and whose signal to noisy ratio is S/N, is given by this equation. Maximum number of bits per second equals B times log 2 1 plus SN ratio, signal to noisy ratio, SN. So this tells us the best capacity that real channels can have. So this for example, For example, here, for example, B equals 3 kilohertz. Okay, B equals 3,000 hertz, and S signal to noise ratio is then what's the maximum number of bits per second? What's the number of bits per second? So the maximum number of bits per second, the maximum number of bits per second is 3,000 times, right, times log 2 1024, right? So right, bit per second. So is 30 kilo bps, right? So if a noisy channel has the bandwidth is 3,000 hertz, signal to noise ratio is 1023, then the capacity of this noisy channel is 30 kilo bps. So this equation, the Shannon theorem, tells us the best capacity of this channel is less than 30 kilo bps. So the next theorem told us for the noisiness channel, maximum data rate equals 2b log 2v. Shannon's theorem told us the noisy channel is maximum number of bit per second equals b times log 2, 1 plus SN ratio. Okay. Then we have introduced the physical media. For example, twisted pairs, coaxial cable, power lines, fiber optics, wireless transmission, and satellite microwaves and infrared transmission, night transmission, the communication satellites, including MEO, LEO, etc. Then we will continue to talk about digital modulation and multiplexing. Wireless and wireless channels carry analog signals such as continuously varying voltage, light intensity, or sound intensity. To send digital information, we must devise analog signals to represent bits. Then the process of converting between bits and signals that represent them is called digital modulation. So, because to send digital information, we must devise analog signals to represent bits. This is called digital modulation. The most straightforward form of digital modulation is to use a positive voltage to represent a 1 bit and a negative voltage to represent a 0 bit. For an optical fiber, the presence of light might represent a 1 bit, and the absence of light might represent a 0 bit. So this scan of baseband transmission is called NRZ. That means non-return to zero. For example, the NRZ scan is shown in the subfig B, non-return to zero. If the bit stream to be transmitted is like this, 1 0 0 0 1 0 1 1 1 1, then we can use these scans using positive voltage to represent a 1 bit, using the negative voltage to represent 0 bit. So negative, positive, positive, negative, 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 positive, negative, then negative, negative, negative. So it's very simple. So it is a straightforward. It is a straightforward form of digital modulation to use a positive voltage to represent a 1 bit and a negative voltage to represent a 0 bit, or to optical fiber, the presence of light might present a 1 bit, and absence of light represent a 0 bit. Once sent, NRZ signal propagates down the wire. At the other end, the receiver converts it into bits by sampling the signal at regular intervals of time. This signal will not look exactly like the signal that was sent. It will be attenuated and distorted by the channel and the noise at the receiver. So it will be the original signal sent at the sender end will be attenuated and distorted by the channel and noisy at the receiver. So to decode the bits, the receiver maps the signal samples to the closest samples. For NRZ, a positive voltage will be taken to indicate that a 1 bit was sent, and a negative voltage will be taken to indicate that a 0 bit was sent. For clock recovery, a clever trick is to mix the clock signal with the data signal by XOR them together so that no extra line is needed. Result is shown in the D subfig D, called Manchester coding, Manchester scams. Manchester scams is like this. From negative jumping to from negative jump to from positive jumping to negative represent a 1 bit. From negative jumping to positive represents a 0 bit. So negative to positive means 0. Negative to positive means 0. Positive jumping to negative. From positive to negative means 1 bit, bit 1. Okay, so this is a Manchester scams. Or use XOR with bits. From negative to positive represents 1 bit. The bit 1. Then 0, then use the same as the former one. From negative to positive, negative, positive. Then if next bit is 1, so will be different. One, so the different from negative to positive. So the 1 is positive to negative. So probably this is wrong. This is wrong. Okay. The scam is called Manchester encoding and was used for classic Ethernet. Often we want to use a range of frequencies that does not start at 0 and send information across a channel. For wireless channel, it is not practical to send very low frequency signals because the size of the antenna needs to be a fraction of the signal wavelength, which becomes larger. So in any case, regulatory constraints and the need to avoid interference usually dictate the choice of frequencies. Even for wires, placing a signal in a given frequency band is useful to let different kinds of signals exist on the channel. This kind of transmission is called passband transmission, because an arbitrary band of frequencies is used to pass the signal. So it's called passband transmission, while the former one is baseband transmission. The absolute frequency value do not matter for capacity. This means that we can take a baseband signal that occupies 0 to B Hz and shift it up to occupy a passband of S to S plus B Hz without changing the amount of information that it can carry, even though the signal will look different. To process a signal at the receiver, we can shift it back down baseband, where it is more convenient to detect symbols. Digital modulation is accomplished with passband transmission by regulating or modulating a carrier signal that sits in the passband. We can modulate the amplitude, frequency, or phase of the carrier sense. Each of these methods has a corresponding name. So, ASK, FSK, PSK, the different names. In ASK, M means amplitude shift keying. Two different amplitudes are used to represent a 0 and 1 bit. An example with non-zero and a 0 level is shown this figure. Okay, this is an amplitude. If the bit stream to be transmitted is 0101100100100100, then amplitude shift keying is like this: 0 having amplitude, 0 having amplitude for 1100. So with a non-zero and a 0 level for 1 and a 0 bit. Similarly, with FS key means frequency shifting keying, 2 or more different tones are used. The example in this figure uses just 2 frequencies, F1, F2. So if we use F1, no frequency, F1, then F2, higher frequency. If we use F1, no frequency, F1 for 0 bit, F2 frequency for bit 1, then 0101 bit, then F2, F1, F2, F1, F2, F2, F1, F1, F2. So it's different the signals with different frequencies to represent the bit stream. So 2 or more different frequency or tunes are used. In the simplest form of PSK means phase shifting key. Shifted keying, the carrier wave is systematically shifted 0 or 180 degrees at each symbol period. Because there are 2 phases, it is called BPSK, means binary phase shifting keying. Here, binary refers to the 2 symbols. Note that the symbols represent 2 bits. Here, binary refers to the 2 symbols. Two symbols means the phase, 0 phase, pi phase, 0 phase, pi phase, so pi phase. So it's systematically shifted 0 or pi at each symbol period. The modulation schemes we have seen that are send one signal to convey bits along a wired or wireless link. However, economies of scale play an important role in how we use networks. Consequently, Multiplexing schemes have been developed to share lines among many signals. So the FDM takes advantage of passband transmission to share a channel. It divides the spectrum into frequency bands, which each user having exclusive possession of some band in which to send their signal. So this is the principles of FDM, frequency division multiplexing. This figure shows the frequency division multiplexing. The original bandwidth is like this: channel 1, 2, 3. The bandwidth raised in frequencies is the multiplexed channel carried includes the three channels like this, because the channels, each channel locates the different frequency points, different frequency band. Then about time division multiplexing. With TDM, users take turns in the round-robin fashion. Round-robin fashion means 1, 2, 3, 1, 2, 3, 1, 2, 3. This is a round-robin TDM multiplex. Each one periodically getting the entire bandwidth for a little burst of time. For getting the entire bandwidth for a little burst of time means for a narrow time slot. For a narrow time slot. So an example of three streams being multiplexed with TDM is shown in this figure. Bits for each input stream are taken in the fixed time slot, and output to the aggregate stream. This stream runs at the sum rate of the individual streams. For this to work, the streams must be synchronized in time. Usually, small intervals of guide times, analogous to a frequency guide band, may be added to accommodate small timing variations. TDM is used widely as part of telephone and cellular networks. The improved version of TDM is dynamic TDM. So the basic TDM is static TDM, while the improved version is STDM, means statistical or dynamic TDM. Statistical TDM means is added to indicate that the individual streams continue to contribute to the multiplexed stream, not on the fixed schedule, not transmitted on the fixed time slot, but according to the statistics of their demand. So STDM is packet switching by another name. Then we have introduced the TDM, FDM. Then the third one is CDM. CDM means code division multiplexing. It is a form of spread spectrum communication in which a narrow band signal is spread out over a wider frequency band. This can make it more tolerant of interference as well as allowing multiple signals from different users to share the same frequency band. Because code division multiplexing is mostly used for the latter purpose, it is commonly called CDMA, code division multiple access. It is widely used for 3G mobile communication. CDMA allows each station to transmit over in the entire frequency spectrum all the time. Multiple simultaneous transmissions are separated using coding theory. The key to CDMA is to be able to extract the desired signal while rejecting everything else as random noise. The CDMA techniques probably is some complex. How to exact the desired signal while rejecting everything else as random noise. That is the key of CDMA. So in CDMA, each bit time is subdivided into m short intervals called chips. Typically, there are 64 or 128 chips per second per bit. Each station is assigned a unique m bit code. Here m can be 64 or 128 m bit code called a chip sequence. It is convenient to use a bipolar notation to write these codes as the sequence of -1 and a +1. So to transmit a 1 bit, a station sends its chip sequence. To transmit a 0 bit, it sends the negation of its bit sequence. No other pattern are permitted. So to transmit a 1 bit, sends its chip sequence itself. To transmit a 0 bit, it sends the negation of its chip sequence. For example, there are 4 stations. There are 4 stations noted by A, B, C, D. A has this chip sequence -1, -1, -1, +1, +1, -1, +1, +1. And then B has this chip sequence. The chip sequence is a unique m bit code. So they have different chip sequence, means chip code. Now in this figure, A and B, here A and B, we show this chip sequence assigned to 4 example stations and the signals that they represent. Each station has its own unique chip sequence. Then this unique chip sequence has some characteristics that is orthogonal. Let us use the symbol S, capital S, to indicate the M chip vector for station S, and S bar for its negation. All chip sequences are pairwise orthogonal, by which we mean that the normalized inner product of any two distinct chip sequence S and T, then written as S dot T. That means normalize the inner product of any two distinct chip sequence S dot T is 0. If S dot T, the inner product is 0, then we say S and T are pairwise orthogonal. It is known how to generate such orthogonal chip sequence using a method known as Walsh codes. In mathematical terms, orthogonality of chip sequences can be expressed as follows: S dot T, inner product, normalize the inner product, equals sigma, then 1 over m times sigma SITI. It should be 0. So note that if ST equals 0, then S dot T bar, then the normalize the inner product of S and T bar is also 0. The normalized inner product of any chip sequence we see itself must be 1, because the SI squared is 1. 1 M ones is M divided by M is 1. So this follows because each of the M terms in inner product is 1. So the sum is M. Also note that S dot S bar means normalize the inner product of S and S bar equals -1. Negative. So negative. So using these characteristics, then if the base station should extract the signal of station A, then the base station use the chip sequence of A in the product, the total of the signal, then it will extract the desired signals, while reject everything else as a random noise, because everything else is T. The S in the product T is 0. So it is some complex but interesting. Then we will talk about PSTN. Nonetheless, the telephone system is tightly intertwined with computer networks. The limiting factor for networking purpose turns out to be the last mile over which customers connect, not the trunks and switches inside the telephone network. This situation is changing with the gradual rollout of fiber and digital technology at the end of the network, but it will take time and money. During the long wait, computer systems designers used to work with systems that give at least three orders of magnitude better performance, have devoted much time and effort to figure out how to use the telephone network efficiently. Soon after Alexander Bell patented the telephone in 1876, just a few hours ahead of his rival, Gray, there was an enormous demand for his new invention. The initial market was for the sale of telephones, which came in pairs. It was up to the customer to string a single wire between them. If a telephone owner wants to talk to N other telephone owners, separate wires had to be strung to all N houses. It's like this. The subfigure looks like the subfigure A, fully interconnected network. So it became immediately obvious that the model of connecting every telephone to every other telephone was not going to work. Right? It in a large scale, it was not going to work. To his credit, Bell saw this problem early and formed the Bell Telephone Company, which opened its first switching office in 1878. The company ran a wire to each customer's house or office. To make a call, the customer would crank the phone to make a ringing sound in the telephone company office to attract the attention of an operator, which would then manually connect the caller to the callee by using a short jumper cable to connect the caller to the callee. The model of a single switching office illustrated in B. So this is improved scams from the original fully interconnected network using the switching office. So opened its first switching office. Okay, let's have a rest for 10 minutes. Okay, let's continue. Okay, let's continue. This figure shows how a long-distance connection might be routed with a typical circuit route for long-distance call. Telephone and office to office, intermediate switching offices. These components of a telephone system. The telephone system consists of three major components: local loop, trunks, and switching offices. Local loops is usually analog twisted pairs going to houses and businesses. Trunks is trunks usually are digital fiber optic links connecting the switching offices. The switching offices where cores are moved from one trunk to another. This is a structure of a typical structure of telephone system. Local loop is also frequently referred to the last mile. Although the length can be up to several miles, it has carried analog information for over 100 years and is likely to continue to do so for some years to come due to the high cost of converting to digital. To send bits over the local loop or any other physical channel for that matter, they must be converted to analog signals that can be transmitted over the channel. This conversion is accomplished using the methods for digital modulation that we studied in the previous section. In the other end of the channel, analog channel is converted back to bits. A device that converts between a stream of digital bits and an analog signal that represents the bits is called a modem, which is short for modulator and demodulator. So convert between a stream of digital bits and an analog signal that represents the bits. Modems come in many varieties. Telephone modems, DSL modems, cable modems, wireless modems, etc. Logically, the modem is inserted between the digital computer and the analog telephone system. This is a computer. The digital and then the analog telephone system. So here. So figure 32 shows the use of both analog and digital transmission for computer-to-computer call. Conversion is done by the modems and the decodes. Computer access the network with an analog local loop by modem. As internet access became an increasingly important part of their business, the telephone company began to realize they needed a more competitive product. Their answer was to offer new digital services over the local loop. So initially, there were many overlapping high-speed offerings, or under the general names of DSL, Digital Subscriber Line, for various ADSL, etc. So services with more bandwidth than standard telephone services are sometimes called broadband. Although the term really is more than a marketing concept than a specific technical concept. So later, we will discuss what has become the most popular of these services. Unfortunately, the capacity of the local loop falls rather quickly with the distance from the end office as the signal is increasingly degraded along the wire. A plot of the potential bandwidth as a function of distance is given in this figure. The increasing curves. This figure assumes that all the other factors are optimal. For example, new wires, modest bundles, etc. Okay, we will not introduce the DSL in detail. If you are interested, you can look at the textbook. Fiber to the home deploy the copper local loop limits the performance of ADSL and telephone modems to let them provide faster and better network services. Telephone companies are upgrading local loops at every opportunity by installing optical fiber all the way to the houses and offices. Result is called FTTH. While FTTH technology has been available for some time, deployments only began to take off in 2005 with growth in demand for the high-speed internet from customers used to DSL and cable who wanted to download the movies. Around 4% of US houses are now connected to FTTH with internet access speeds up to 100 megabps. This figure 36, shows the passive optical network for fiber to the home. This architecture is called a POM, passive optical network. It is common to use one wavelength shared between all the houses for downstream transmission and another wavelength for upstream transmission. Trunks in the telephone network are not only much faster than the local loop, they are different in two other respects. The core of telephone network carries digital information, not analog information, that is bits, not voice. This necessitates a conversation at the end office to digital form for transmission over the long-haul trunks. The trunks carry thousands, even millions of calls simultaneously. This sharing is important for achieving economies of scale, since it costs essentially the same amount of money to install and maintain a high bandwidth trunk as a low bandwidth trunk between two switching offices. It is accomplished with versions of TDM and FDM multiplexing. So early in the development of telephone system, the core handled voice calls as analog information. FDM techniques were used for many years to multiplex 4,000 Hz voice channel into larger and larger units. For example, 12 calls in the 60 kHz to 108 kHz band is known as a group, and 5 groups are known as subgroup, and so on. These FDM methods are still used over some copper wire and microwave channels. However, FDM requires analog circuitry and is not amenable to being done by a computer. This is about digitizing voice signals. The codec makes 8,000 samples per second because next theorem says that this is sufficient to capture all the information from 4 kHz telephone channel bandwidth. At a lower sampling rate, information would be lost. At a higher one, no extra information would be gained. Each sample of the amplitude of the signal is quantized to an 8-bit number. This technique is called parse code modulation. It forms the part of the modern telephone system. So the PCM is a core technique of the modern telephone system. The standard uncompressed data rate for a voice-grade telephone call is thus 8 bits every 125 seconds, or that is 64 kilobps data rate. This is about time division multiplexing. TDM, time division multiplexing based on PCM, is used to carry multiple voice calls over trunks by sending a sample from each call every 125 milliseconds. The method used in North America and Japan is the T1 carrier, depicted in the figure 37. T1 carrier consists of 24 voice channels multiplexed together. Each of the 24 channels in turn gets to insert 8 bits into the output stream. So this is about time division multiplexing. Then Sonnet. We will not introduce this foundation communication in detail. This is about the physical channel. So it is not the key to our computer field. Okay, this is a wavelength division multiplexing, a form of frequency frequency division multiplexing is used as well as TDM to harness a tremendous bandwidth of fiber optic channels. It is called WDM. The basic principle of WDM on fibers is depicted in figure 41. Here, four fibers come together. Four fibers, fiber 1, 2, 3, 4. Four fibers using lambda wavelengths, lambda 1, 2, 3, 4. So four fibers come together at an optical combiner, each with its energy present at a different wavelength. The four beams are combined onto a single shared fiber for transmission to a distant destination. At the far end, there is a splitter. So at the far end, the beam is split up over as many fibers as there were on the input side. Each output fiber contains a short, specially constructed core that filters out all but one wavelength. So this is a wavelength. The resulting signal can be routed to their destination or recombined in different waves for additional multiplexed transport. WDM technology was invented around 1990. The first commercial systems have 8 channels of 2.5 gigabit per second per channel. By 1998, the systems with 40 channels of 2.5 gigabit per second were on the market. So the WDM technology develops very fast. When the number of channels is very large and the wavelengths are spaced close together, the system is referred to as DWDM. Means here D means dense WDM. Now we will introduce a new concept about switching. 2 different switching techniques are used by the network nowadays, circuit switching and packet switching. Circuit switching is traditional. It came from traditional telephone system. Traditional telephone system is based on circuit switching, but packet switching is beginning to make inroads with the rise of voice over IP technology. Both kinds of switching are important. Conceptually, when you and your computer places a telephone call, the switching equipment within the telephone system seeks out a physical path all the way from your telephone to the receiver's telephone. This technique is called circuit switching. It is shown schematically in figure 42. Subfigure A shows circuit switching. That means from the sender to the receiver, there should be a physical channel, should be a physical circuit. Each of the 6 rectangles represents a carrier switching office. The carrier switching office or switching boxes. switching boxes represent the carrier switching office. Probably is an office or tour office, etc. In this example, each office has 3 incoming lines and 3 outgoing lines. This is a circuit switching usually used in telephone systems. But in the computer network, packet switching is widely used. When a call passes through a switching office, a physical connection is established between the line on which the call came in and one of the output line, as shown by the dotted lines. The dotted lines. Okay, this is a switching circuit. The basic idea is once a call has been set up, a dedicated path between both ends exists and will continue to exist until the call is finished. An important property of circuit switching is the need to set up an end-to-end path before any data can be sent. So important property of circuit switching is the need to set up an end-to-end path. It should be physical path, end-to-end, before any data can be sent. The elapsed time between the end of dialing and the starting of ringing can easily be 10 seconds. More on long distance or international calls. During this time interval, the telephone system is hunting for a path, as shown in 43A. This figure shows the timing of events in the circuit switching. For example, at the beginning of the communication, 2 ends should establish a physical connection. It will take several seconds. The alternative to circuit switching is packet switching. With this technology, packets are sent as soon as they are available, not like the condition of this. Before any data can be sent, the connection should be set up in circuit switching. But for packet switching, there is no need to set up a dedicated path in advance. So it is unlike with circuit switching. It is up to routers to use a store and forward transmission to send each packet on its way to destination on its own. This procedure is unlike circuit switching, in which the result of the connection set up is the reservation of the bandwidth all the way from the sender to the receiver. All data on the circuit follows this path. Among other properties, having all the data follow the same path means that it cannot arrive out of order. So this is the most advantage of the circuit switching. Among other properties, having all the data follow the same path means it cannot run out of order. That means all paths arrive in order in circuit So figure is unlike circuit switching. With packet switching, there is no fixed path. So packet switching, there is no fixed path. So different packets can follow different paths depending on network conditions at the time they are sent, and they may arrive out of order. So that is are the differences. These are differences between packet switching and circuit switching. Packet switching networks place a tight upper limit on the size of packets. This ensures that no user can monopolize any transmission line for very long, so that packet switching networks can handle interactive traffic. Packet switching and circuit switching also differ in other ways. For example, queuing delay, congestion control, etc. Because no bandwidth is reserved with packet switching, packets may have to wait to be forwarded. This introduces queuing delay and congestion if many packets are sent at the same time. On the other hand, there's no danger of getting a busy signal and being unable to use the network. Thus, congestion occurs at different times with circuit switching and packet switching. If a circuit has been reserved for a particular user and there's no traffic, its bandwidth is wasted. It cannot be used for other traffic. Packet switching does not waste bandwidth, and thus is more efficient for a system perspective. So they differed in these ways. Packet switching is more fault tolerant than circuit switching. That is the reason why the military network is based on packet switching techniques. The differences are summarized in figure 44, including core setup, a dedicated physical path. Each packet follows the same route. Packets arrive in order or out of order. Is a switching crash fatal, bandwidth available, time of possible congestion, potentially wasted bandwidth, store and forward transmission, charging. Here, charging refers to charging fee of network usage, according to network using. Charging, not the power charging. Then the mobile telephone system. Mobile telephone system will introduce to some concepts. Introduce some concepts. People now expect to make phone calls and to use their phones to check email and surf the web from airplanes, cars, swimming pools, and while jogging in the park. Consequently, there is a tremendous amount of interest in wireless telephony. The mobile telephone system is used for wide area voice and data communication. Mobile phones, sometimes called cell phones, have gone through 3 distinct generations. Probably here 3 should be updated to 5 or 6 distinct generations. 5 distinct generations, widely called 1G, 2G, 3G, 4G, 5G, and beyond. The generation listed as 1G using analog voice transmits analog voice. 2G transmits digital voice. 3G transmits digital voice and data, usually for internet access, email, etc. Surf the web from 3G. In 1960s, IMTS means Improved Mobile Telephone System was installed. It used a high-powered 200-watt transmitter on top of the ear, but it had 2 frequencies, one for sending and one for receiving. AMPS, invented by Bell Labs, and first installed in the United States in 1982. In all mobile phone systems, a geographic region is divided into cells, which is why the devices are sometimes called cell phones. In AMPS, the cells are typically 10 to 20 kilometers across. In digital systems, the cells are smaller. Each cell uses some set of frequencies not used by any of its neighbors. It's like this. This figure 5, shows the frequencies. For example, A used in this figure in frequency A used in cell A, then not reused in adjacent cells. Adjacent cells then should use different frequencies. The idea of frequency reuse is illustrated in A. The cells are normally roughly circular, but they are easier modular as a hexagon. The cells are all the same size. They are grouped in units of 7 cells. Each letter indicates a group of frequency. Okay. Notice that for each frequency set, there is a buffer about 2 cells wide where that frequency is not reused, providing for good separation, no interference. In an area where the number of users has grown to the point that the system is overloaded, the power can be reduced, and the overloaded cells split into smaller microcells to permit more frequency reuse, as shown in Figure B. The second generation is digital. Switching to digital has several advantages. It provides capacity gains by allowing voice signal to be digitized and compressed. It improves security by allowing voice and control signals to be encrypted. This in turn determines deters fraud and eavesdropping, whether from intentional scanning or echoes of other calls due to RF propagation. Finally, it enables new services such as text messaging, such as just as there was no worldwide standardization during the first generation, there was also no worldwide standardization during the second. Several different systems are developed, and 3 have been widely deployed. DMPS, GSM, CDMA. Here, GSM means Global System for Mobile Communication. CDMA means Code Division Multiple Access. The third generation of mobile phones of all 3G, as it called, is about the digital voice and the data. The number of factors are driving the industry. First, the data traffic already exceeds voice traffic on the fixed network and is growing exponentially, whereas voice traffic is essentially flat. Second, the telephone, entertainment, and the computer industries have all gone digital and are rapidly converging. Many people are droning over lightweight, portable devices that act as a telephone, music and video player, email terminal, web interface, gaming machines, and more, all with worldwide wireless connectivity to the internet at high bandwidth. So ITU community, ITU tried to get a bit more specific about this vision starting back around 1992. It issues a blueprint for getting there called IM 2000. The basic services that IMT 2000 network was supposed to provide to its users are high quality voice transmission, supporting messaging, multimedia, internet accesses, etc. Now, that's all for today. Next time we'll continue. We'll continue to talk about other techniques. That's all. That's all for today. Thank you. Bye.